All right, we're going to introduce our next speaker, Bob Fruth. He's actually spoken at BSides last year as well, and it was really well received. I really liked it. So this year, he's going to be talking about threat modeling in the age of connecting to everything, which is incredibly relevant considering everything that we know of and love is getting an IP address. So let's give a warm welcome to Bob Fruth.
Thank you, Alex. So before I launch into slides, I have a question. How many of you have created a threat model? Okay, for those of you who have, you may get some review. And for those of you who haven't, this might be new material. So I'm Bob Fruth. I'm a Security and Privacy Program Manager. I'll note that the opinions you're hearing from me today are mine and not indicative of current, future, or former employers or clients. We'll talk a bit about why you threat model, cover some basics of threat modeling and data flow diagrams, talk about identifying threats and proposing mitigations, and then I actually did a kind of a high-level threat model on a car, because that's what really piqued my interest that led to this talk. So who am I? I've been at Microsoft a long time. Before Microsoft, I worked at several different companies down in Silicon Valley, a bunch of market-leading products. If any of you have heard of Harvard Graphics, I was on that team. That's a long time ago now. Done a bunch of stuff at Microsoft you can read, so I won't bore you with telling you about it, but I will say that the threat modeling bug bit me over 10 years ago, and my family watches me carefully going through airport security to make sure I'm not threat modeling it as I go through it. So why should you threat model? Well, threat models find serious problems. If you ship a security design bug and it impacts your customers, you have a problem. You've got direct and indirect costs. There's the cost of response, which we just heard from the sponsor about some of that cost of response. You've got product and brand reputation, and that's huge, especially in this day of the internet where you make a faux pas, the world knows about it. Even people who have no idea what your company does or your product does or your service does, they will know that it had an issue. You've got cost to customers, and if customers get really ornery if your product or service costs them money other than what they're thinking that they have to pay you. So again, a lot of indirect and direct costs. One of the goals of threat modeling is to design products and services that are secure by design. So you want to understand what things you're exposing, what your attack surface is, what interfaces or what have you that attackers can get to. You want to understand where you've got levels of trust and, more importantly, boundaries between levels of trust. And we'll talk about this in a little more detail in a bit. The other thing, and I will reference Robert's talk yesterday, attackers think strategically. They only have to find one flaw. You have to find all of them. And all of us, when we work on a product or a service, we have creator blindness. Our baby is the most beautiful thing ever. Attackers don't care how pretty your baby is, they want to find the ugly bits. So you've got to overcome creator blindness and get some new perspective, and threat modeling can help you do that. And finally, it allows engineers to find and effectively find security problems early in the process. Goals of threat modeling: you want to describe product security in a structured way. I've mentioned documenting attack surfaces, security relevant features, that's kind of important to understand. Potential threats against resources, what those resources are, what assets you're protecting, what mitigations you can apply against those threats, and ultimately threat modeling is kind of like insurance. It's a risk proposition. You threat model so you understand risk, and then you can assess that risk and say, okay, this is what we need to do or not do in response to it. So when should you threat model? I claim you should do it early. If you find a design flaw at design time, you can fix it right then. Many vulnerabilities are built in during design time, and I've heard 50%, 70%, high percentages. On an ongoing basis, if you threat model early especially, you can revisit your security, maintain your threat models, you maintain your specs or your API documents, or you can threat model late. Higher cost to fix, more disruptive to your release cycle. Or you can release with known vulnerabilities. That's a real great story for your customers. And I'll note that some vulnerabilities cannot be patched. The industry as a whole has struggled with how to release patches for firmware, for example. The example I've got a little later, very difficult to patch, although there is one way to do it. You'll see it when we get to it. And you can defer your design changes to next release. Then some attacker finds your design flaw, exploits it, and your customers are sending you email, making phone calls, and worse yet, abandoning you for your competitor. So I have a question. Are automatic tellers secure? There's one outside in the lobby out in the bar there. So the late Barnaby Jack hacked an ATM network on stage at Black Hat in 2010. That's 4.5 years ago. I still love this example. I'm sparing you the video off of YouTube. You can find it. Go to YouTube, search for Barnaby Jack. You'll see it. Here's a picture. Those are $1 million bills on the floor. They have his image on them. He hacked the ATMs. A Black Hat audience, which is fairly staid, clapped and cheered. He had loopy music playing in the background, which is kind of cool too. It is Vegas. All the slot machines make loopy music. So what's wrong with an ATM? The money is in a safe. It should be safe, right? Well, the computer that controls the spitting out of the money may or may not be in a safe. Okay. The connectivity to the ATM itself is not in a safe. Otherwise, it would not be connectivity. So kind of by design. In the case of many of ATMs, especially standalone models, the key to get inside the ATM is the same. The ATM companies figure, well, I've got some guy servicing 3,000 ATMs or whatever number they service. They want to juggle 3,000 keys. We'll give them one. The passcode is not changed on a regular basis or not changed at all. You can find the defaults on the internet. And the particular flaw that Barnaby used to update the firmware was very simple. The firmware update process was based on bad crypto. I don't know exactly what algorithm was involved. It hopefully was something as recent as MD5, but who knows. Barnaby found that anybody could install their own ATM software if they could get to that connectivity. A threat model could have saved them. I can see this threat model in my head. I could see it back when I first saw the video of Barnaby and saw him at a subsequent event demoing the same demo. So what else can you threat model? Simple web apps. Okay, that's kind of vanilla at this point. Apps on your devices. We all have phones. We all have smartphones. We all have apps on them. Complex systems. Internet retailers. Front ends, back ends, both together. Large search engines. I happen to think about that one fairly constantly. Your child's doll. This is Kayla. It's marketed in the UK. BBC News. Late last year, talking doll Kayla is hacked. What did she say? Gee, as a parent, do you really want to have your children's doll saying things that probably aren't appropriate for your son or daughter? Or your car. This is what piqued my interest. A General Motors ad that was talking about Wi-Fi hotspots in your vehicle. Gee, driving down the street, surfing the internet. Or maybe your passengers are, because if you're driving, you probably shouldn't be. Yeah, we'll get to this. And this actually, I saw the ad in the United States, but this is from the Canadian General Motors website. All right, let's talk about some threat modeling basics. Threat models are effective when there's a network involved, or the web. Multiple user contexts or privileges are present. So for instance, if you have administrative mode versus non-administrative mode, or guest versus system, or what have you, multiple processes sharing information, and I would claim that most anything that is at all interesting has multiple processes involved. Layered architectures. At a historical point, the threat models originated in the 3-tier client-server enterprise applications. In this day and age, those applications are pretty well understood. The threat model can be described relatively simply, but we've gone beyond that. You need to remember what it is you're protecting. Secrets, those are kind of important. Customer data, gee, financial data, medical data, that's kind of really important because there's all kinds of things like legal ramifications and regulatory ramifications, especially with medical or financial data. Yeah, let's lose our customers' credit cards. And we all know about all the well-known hacks and breaches where that has happened. Child's privacy. Child safety controls. When I look at that Kayla doll, I'm immediately thinking, okay, if a parent, what control does that doll give the parent? The responsiveness of a car to the driver. That's kind of important in the car example. So I've talked about this already, what you can find by threat modeling, design problems which you can correct early, preferably before you get too deep into coding. You can quantify and qualify your attack surface, figure out what your risky areas are, what your not so risky areas are. Robert in his talk yesterday talked about aspects of the threat model where you choose not to mitigate. You have to know what those aspects are in order to make that decision. You have to figure out what inputs you're taking from either the web or from a user or from an administrator. And I claim that if it's coming from anywhere outside of the system, you assume it is evil. You hate calling your users and your customers evil, but you have to figure that their data might be. And finally, early awareness of implementation gotchas. In the web space, knowing that you have a SQL backend is a really useful thing to know so you can mitigate against SQL injection. You need to set expectations when you create a threat model. Figure out what you can't protect against. Can you protect against evil administrators? I've always claimed that an evil administrator is not a technical problem, it is a management and human resources problem. But it's still something that we should mitigate against as much as we can. What about physical possession? You know, one of the immutable laws of security is if somebody has your device, it's no longer your device. Now we're moving into the realm of BitLocker and trusted modules and so forth. That particular rule's quite not as strong as it was. You need to know what you're dependent on. You may or may not be able to control how you use it, but you need to know what it is and understand the properties. You know, OpenSSL is a fine library. If you depend on OpenSSL, it's good to know that you're making that dependency, because when OpenSSL gets broken, you can take appropriate action. Finally, part of doing a threat model is listing your assumptions, and then you go back and validate them. So, data flow diagrams efficiently represent something: a system, a component, an app, a feature, a car, a doll, a web app, a phone app, the smartphone itself. You include processes, data flows, data stores, and trust boundaries, and we'll talk about each of these in a little bit. You can create a data flow per every scenario. You can do it per system, per component. It's pretty flexible in that way. I've talked about assumptions and dependencies already. Here are your basic elements. Processes do things to things. The part of a car that controls braking is a process. The web browser is a process. You could claim that the operating system underneath the web browser is a process as well, although you quickly would disseminate it into a whole pile of processes. You have users and external entities. These are things outside the system that impact it or that are served by the system, users being the classic example. You have data stores, which can be anything from files to registries to databases to what have you, and then you have data flowing through all of these things. In threat modeling, we use dashed lines to indicate location of trust boundaries and diagrams. You can also use them to indicate process boundaries, system boundaries, etc. The key here is, I'm talking specifically of trust boundaries, the key is that the trust boundary marks where you've got a trust difference or where there is a trust decision that is made as the data flows across that boundary. Data originating outside the boundary is untrusted. If you have data that you originate inside the trust boundary and traverse it outside, it's no longer trusted because it's gone outside your trust boundary. The question you ask with trust boundaries is, what interfaces are you exposing? So, you add your trust boundaries to your diagram. We'll talk about diagrams and actually look at a diagram in a moment. You evaluate your users and external processes. You don't trust users. Do you trust administrators? That's a question. That's a risk question. How much do you trust external processes? In some regards, if you're writing an app for the iPhone or the Android phone or the Windows phone or the BlackBerry, you have to trust that those platforms do what you expect them to do. We've talked about where data comes from. You have to figure out whether you trust it or not. The key point of this slide is that trust is relative. You're moving data from one trust level to another. It's a relational thing. So here's a diagram of a simple web server. I'm almost embarrassed to display this because it's so bloody simple. You've got the browser on the left. It talks to the web server back and forth. You assume that that there is a user using that browser, traversing the internet, making authentication, authorization claims and calls and decisions and so forth. On the back end, the web server talks to an administrator. Now, the administrator probably is assumed to be in the same environment as the web server. You'll notice there's another trust boundary there where there's some authentication and authorization step that is done. That administrator is logging into the web server, into whatever management console it provides, and there's some way of authenticating with that and some way of being authorized for it. At least you hope so if you're actually deploying this in your environment. So with data flow diagrams, you do multiple levels. You start off with a context diagram. That previous slide was an example of a context diagram, very high level. Your processes represented by, or your target system represented by a single process bubble or circle or what have you. It describes the overall system. You then move to a level 0, and I have an example of these later on in the talk, showing major subsystems. And then you go on down to level 1, level 2, level 3, level N, what have you, showing the components of each of those processes or the process that you're threat modeling, moving on down. Often you'll find that the context diagram and the level 0 diagram are one and the same, and that's fine. The key here is to be accurate and complete, not to draw lots of pretty pictures needlessly. So how many levels do you need? Well, you always need to create at least one diagram, otherwise why bother? Level 1 diagrams are good for creating, to model complex subsystems. You need to use enough levels to understand those subsystems and the risks. If you get to a point where, say, you're doing a complex system, you're down at level 5, and you get to a diagram where you've got a subsystem with no trust boundaries, you're done. A diagram with no trust boundaries is kind of boring because there's nothing to talk about there. If you understand the risks, you've gone deep enough. And there's no real rule I can give you about when you say I understand the risk well enough, except to kind of, as you work through the threat model, you've got to a point where it's like, okay, here are a bunch of risks articulated, here's some vulnerabilities, here's some mitigations, I think we're done. And then you have somebody else look at your work and ask them whether they think you're done. Some basic rules. With external entities, traditionally data flow between external entities was outside the scope of diagrams. So for instance, you never assumed when you're modeling a complex client server application that the end user and the administrator actually ever talked. Now, external entities can only talk to processes because ultimately the entity does something to data by a process to some regard. The rules for external entities have changed somewhat with the Internet of Things. You need to consider data flow between external entities when you threat model something that's Internet of Things. So that rule has changed. Flows are unidirectional. Data flows from one point A to point B, or from process A to process B, or from process B to data store C, or from process B to end user Bob. They don't flow the other way. There's a separate data flow that flows back. Some basic rules on processes. A process without input is a miracle. How did it actually make data from nothing? A process without output is a black hole. Gee, let's send data to this process and drop it. And it's like, why bother sending the data at that point? The process does something with it. It stores it somewhere, it displays it to somebody, it munges it and sends it back. That's a great question, and actually repeat that question when I pull the demo up in about 20 minutes, because there is a part in the diagram where I violate that rule completely. A good question. The question is, what happens if you have a process that just ends for later functionality? Some basic rules with data stores. Data stores don't move data. Data stores get data written to them, and they provide it for reading. Processes get and put data. And I've already talked about end users and external entities don't access data stores directly. Even if you think of the manual process of taking a piece of paper and putting it into a filing cabinet, you are the end user, you are the external entity, the filing cabinet is the data store, but the act of putting the paper in the filing cabinet is the process. Although how many of us have filing cabinets anymore? Some common problems. If you have too many processes in your diagram, you're probably drawing level 2 detail in a level 1 diagram. You'll know. If you can't look at a diagram and kind of see the whole thing, you probably have gotten too far down in the weeds. If you've got overly complex data flows, this picture here, for example, probably may indicate a fundamental design problem, or may indicate that you need to move up a level and do the previous level diagram first. If you cannot document your product or service with a data flow diagram, it will be very difficult to threat model, and it will be very difficult to secure. So in summary, data flow diagrams are an effective modeling tool. Trust boundaries highlight relationships between things. Data flow diagrams make your team think through what it is they're designing. And the technique has proven very valuable in understanding attack surface. So let's identify some threats and talk about vulnerabilities and mitigations. The process is in a nutshell. You have a vision of what you're building, you start to design it, you create your diagram, you identify threats, you mitigate, you validate the mitigations, and you rinse and repeat next release cycle. Mitigation is the point of threat modeling. You address or alleviate problems, you protect your customers and their data, you want to design as secure product or service as you can. You know, why bother? You create a great threat model. Gee, we had lots of threats and we have beautiful diagrams and it's all nicely documented and it's accurate. And then you don't do anything else. You find the point is you want to find the problems and fix them. So for threat identification, I use the STRIDE model. There are other nomenclatures out there. I'm familiar with STRIDE, so that's what I've chosen to talk about. STRIDE is an acronym for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. They all refer to properties that you want. These are threats against those properties. Let's talk about some details. So spoofing is the act of impersonating something or someone else. It is an attack against authentication. You're pretending to be a specific web service or pretending to be Bill Gates. I don't think Bill's here today, so we can all pretend to be Bill, I guess. Tampering, modifying data or code. It's an attack against integrity. Modifying a packet as it traverses the network in your building, the network over the internet, the network in the car, what have you. Repudiation is probably the most difficult to understand. It's claiming to not have performed an action, and the property you're attacking is non-repudiation. Examples, I didn't make that change. In software and services, the main mitigation for repudiation is to log everything. I didn't make that change. Well, that's nice. Here we have the log on source control that shows you did. Last Tuesday at 3 o'clock in the afternoon. Information disclosure is the privacy-related type of vulnerability or threat. It's exposing information to somebody who's not authorized to see it. It is an attack against confidentiality. Very important in this day and age of privacy. Denial of service is pretty self-explanatory. It's to deny or degrade service to end users. It's attacking the property of availability. And finally, elevation of privilege is attacking authorization. It's where you get capabilities where you aren't authorized to have them. And the classic examples are a remote user running commands or going from limited user to root. If you can get root on a system where you started out as guest, you've definitely done some elevation of privilege. So you've got your diagram, you use your trust boundaries in your diagram to analyze the data flowing from one trust level to another, especially when to be wary of trusted processes reading data from untrusted processes. assume inputs are evil, or highly trusted processes running too low. And we've had many examples where a highly trusted process has put out a very informative error message to a not as highly trusted process, which has then used that information to carry out an attack. So let's do a mitigation example. The threat is that my car is parked out front, it's going to get stolen. Somebody's going to open the door and steal the car, start it and steal it. Well, I can mitigate it somewhat if I lock the doors. Well, but the thief could pick the lock. Or I could leave the door unlocked, which is kind of a deployment issue, if you will, an operational issue, because I didn't use the mitigation that was provided. Then the thief could pick the lock, hotwire the car, whatever. But we can mitigate this. Most modern automobiles require a fob, which is an electronic code that between the fob and the vehicle that blocks the ignition without that fob being present. So the thief comes along with a tow truck. And there's your vulnerability. You get towed. Or do you? You could get a hold of a wheel restraining device and put that on your car, which would make it much more difficult to tow. So you've come up with a list of threats using the STRIDE acronym or whatever nomenclature you want to use. Now you need to address them. The whole point of coming up with this set of threats is to actually go through and mitigate them. There are 4 basic ways to mitigate a threat. You can redesign to eliminate. This is a fine thing to do. It is much easier to do it during design time than to do it a week before you ship something pretty huge. You can apply standard mitigations. The classic example in web traffic is using HTTPS instead of HTTP. What if you're building something, what if similar apps, components, systems, services, etc. done? Has that mitigation worked out for them? And actually in the backup slides on the talk, I've got some example mitigations, so I want to make that note. You can invent new mitigations. Not always easy. Might require some specific knowledge or skills. I mentioned HTTPS and HTTP. HTTPS is built on crypto. Crypto is a very specialized skill. Any number of us have seen people do it poorly. Or you can accept the vulnerability. Gee, we have this design issue we cannot mitigate. We are choosing to release with that vulnerability. You assess the risk. How likely are users to be impacted by this? If they are impacted, what is the extent of that impact? You discuss that issue with your management, with customers, and help them make the informed decision. At that point, your work is done. Here's the vulnerability, here's the risk, here's my recommendation. It's a business decision at that point. The customer may look at you and say, we can't accept that risk. Management may look at you and say, our customers can't accept that risk. Or management may look at you and say, we can't accept that risk because if we have to go back and patch, it will cost more than it would cost to redesign now. Okay, so you've got your threat model, you've got a bunch of threats, you've got mitigations, now you need to validate it. Does the data flow diagram match what you built? If it doesn't, you've just threat modeled something else. Have you enumerated your threats? And tools are very useful for doing this, and I'll demo a tool in a moment. At a minimum, you have the STRIDE per element for every element that touches a trust boundary or is adjacent to a trust boundary, or especially the flows that go across trust boundaries. And the threats describe the context, the attack, the vulnerability, and the impact. If you're working with a test engineer or a test group, did they participate in developing the threat model? Full disclosure, I'm married to a test engineer. In fact, she tested my code at one point in our careers. She found some good bugs. They got fixed. Test has a different perspective. They like breaking things. They find issues. They ask questions you don't want, that you as a developer or a program manager or designer or architect don't necessarily want to answer, that make you squirm. The point is that if they ask those questions and you answer them, you have a better product or service on the back end. And of course, a good test engineer can take a threat model and say, here's the vulnerabilities, here's the mitigations, here's the test cases. Very straightforward process. Okay, you've listed a bunch of threats. Have you mitigated them? Do the mitigations describe what you're going to do to mitigate? Did you implement them correctly? Do they work? Can you prove that they work? If you can't prove they work, I would claim that you probably didn't mitigate correctly. Did you check these early? If you did, your release time frame will be more predictable and you'll have fewer all-nighters. If you are working on a complex schedule or multiple releases, what's your plan for rechecking the mitigations as you update your product or service? You want to validate that you've got your dependencies all listed, you know what they are, you know what security functions you're depending on. And I would actually say, are you sure of that? And why are you sure? And then you've made some assumptions. Things that you noted when you were developing the threat model. Gee, SSL v3 is secure. Well, it used to be. I claim that that's no longer a valid assumption, as evidenced by some of the stuff that was announced in mid-October. In the Windows space, a valid assumption today is that crypt-gen random gives us strong randomness. I know several engineers on the Windows team who have staked their careers on that. If it isn't true, then it's a bigger issue than any individual product. If the design changes, you update the design spec, you update the threat model, you update the test cases, repeat the validation process. My point here is that a threat model is like a design spec or an API spec or documentation in your product. It is as living as the product itself. Okay, I talked earlier about threat modeling a car. I've got a simple threat model I'll show you in a moment. Threat modeling tools have come a long way in the past 13 years. I know this for a fact because I used a version 1 threat modeling tool where the most important thing that it did was that it generated a report at the end so I could look at it and say, yes, we threat modeled. The process of getting to the point where I could generate that report was extremely painful. I would say, I recommend always choose tools that meet your goals. I happen to like this particular threat modeling tool because I'm very familiar with it. It has met my needs. Your mileage may vary. I learned to threat model at Microsoft, so I use the Microsoft threat modeling tools. The one you're about to see is available on the web on Microsoft.com, and the URL for getting it is in the deck. Okay, so now I'm going to get out of PowerPoint mode for a moment. And I'm going to bring this, oops, it'd help if I'd bring it up the right way. So this is the Microsoft SDL threat modeling tool, 2014. Which is basically a version 4 tool. Here I have threat modeled a car, or actually parts of a car, and I've simplified it greatly because, frankly, with the research I did showing that most cars have about somewhere between 50 and 100 electronic control units, that's a lot of threat models. But we're gonna, since it was Wi-Fi that kind of piqued my interest, we're gonna focus on the Wi-Fi. Unfortunately, the screen resolution, I can't show you the entire threat model, entire diagram at once, so bear with me as I scroll you through it. This is the human user, the driver or a passenger. And this is the context diagram, sorry. This is the high-level diagram. The human user will do only a couple things. They may have a smartphone app that they can talk to control the car, or they'll have a bunch of manual controls. Gee, a key in the lock, press the ignition, put the car in drive or in first, let out the clutch, turn the steering wheel, turn on the headlights, apply the brakes, check the tire pressure, what have you. The smartphone app will talk over the cellular network to the vehicle, whatever vehicle wireless interfaces the vehicle exposes to that network. We could do a whole threat model just on this piece here, the smartphone network and the cellular carrier and the interface to the car, but we're not going to do that here. Within the vehicle physical boundary, you've got the manual controls and display. You've got vehicle systems. I alluded to a number of these: braking, steering, ignition, tire pressure. You've got the wireless interfaces to those systems, as well as the manual interfaces to those systems. You know, if you apply the brake pedal, you expect the braking system to actually do something. If it doesn't, that's either a vulnerability or time to take the car to the shop. On the back end, also talking these wireless interfaces, are a bunch of services over the internet, which is a trust boundary. This, frankly, scares me because the internet is both wonderful and beautiful and really evil. So a couple other things about this diagram. It's actually, I've left out a lot of detail. It's a context diagram after all. You'll notice in this particular tool, the human user is in gray. I have grayed out the human user because I will claim you can't threat model humans. And actually, if I make the properties window bigger, you'll see. I'm going to assume the driver is authenticated and authorized to the car. And actually, I'll show you in a moment, I have that assumption documented. Similarly, the smartphone app, the cellular carrier, I've grayed them out. We're not threat modeling those in this threat model, so they're out of scope. That's called, we're defining your scope, knowing what it is you're trying to do, what you're threat modeling here, and what you're not going to do. And I've also grayed out the World Wide Web and the services, because again, this threat model is about the car. It's not about the services that are talking to it. I would actually claim that nobody has actually threat modeled the World Wide Web. I'm not sure you could. I suppose you could do a context diagram. It would be rather complicated. So that's a level 0 diagram, basic, high level. I've lumped every system in the car into one process bubble. Lost my mouse there for a moment. Level 0, again, highly simplified. There's our human user. Now, the user is the driver or a passenger. You know, they've got some physical possession. That's a trust boundary. I have the key or the lock to unlock the car or the fob or what have you. I can start the car with that fob or key. If I press the brake pedal, the brakes get applied. You'll notice I have left out a whole bunch of detail. All of these are unidirectional data, well, all unidirectional data flows. There's no return flow. I've left that out because it's not important for this particular threat model. And to the gentleman's point here, here's the braking system, which is a black hole. For the purposes of this threat model, that's fine. I'm not threat modeling the braking system. What I've left out here on the back end is that the braking system actually applied the brakes. And you could claim that the brakes are an external entity, or you could represent them as an external entity, perhaps as a data store or something. So, but the braking system is a great thing to consider when you're threat modeling an entire car, because if you are able to get from Wi-Fi to the braking system, that's a pretty cool thing from an elevation of privilege perspective. Terrifies me. Okay, so let's go on here. And somehow I have messed up there we go. Scrolling to the right. Okay, at the bottom here you have human user, whether it's the driver or the passenger. They're providing human input to their device, their smartphone, their tablet, whatever it is they're going to use the onboard Wi-Fi to talk to the web. The user's device, again, is out of scope. We're not threat modeling your iPad here. We're threat modeling the car's Wi-Fi system. That Wi-Fi device talks to the onboard Wi-Fi, probably over some sort of an authentication and authorization step or boundary. I would certainly hope that was the case. And then that onboard Wi-Fi, through whatever means, whether it's a cellular carrier or OnStar network or some signal, eventually talks to the World Wide Web. So let's go on down to the onboard Wi-Fi. Again, here's our human user. Here's their device. Here's where they're talking to the onboard Wi-Fi over an authenticated and authorized trust boundary. That onboard Wi-Fi hotspot, how is it protected? Now, I will admit, I haven't gone and read the specs or gotten a hold of a manual for whatever late model General Motors car it is that is advertising onboard Wi-Fi, but I would hope that they don't permit customers to set their onboard Wi-Fi to have no authorization and authentication? I suspect they probably do, because the average driver doesn't really want to bother with all that stuff. They just want it to work. And of course, if they can make it work without authentication and authorization for their passengers, they can also make it work without authentication and authorization for anybody who's standing outside the car, whom they've never met before, who may have different motives. Okay, so the onboard Wi-Fi is talking to the World Wide Web over some sort of set of trust boundaries. The internet as a boundary. You hope that this is somehow authenticated and authorized. But the other interesting thing is that your onboard Wi-Fi is talking to the World Wide Web. What else is the onboard Wi-Fi talking to in the car itself? If I can get on the onboard Wi-Fi and talk to other systems in the car, that's kind of a bad thing. I could talk to the tire pressure system. That'd be kind of cool. I could tell the user their tires were fine when they happen to be flat. Or I could tell them they're flat when they happen to be fine. Or I could tell the braking system to apply the brakes every time the car goes over 5 kilometers an hour. Again, the point of this threat model, what piqued my interest was, gee, onboard Wi-Fi, what could possibly go wrong? By threat modeling, it's like I'm raising a whole bunch of questions. I would hope that the automotive industry has done this kind of analysis. I suspect that a good number of the manufacturers have, because if they haven't, I think their legal departments would probably advise them of the liability involved. But that advertising really just raised some questions in my mind. And ultimately, when it comes to a vehicle, the most important things to me is that it starts when it needs to start, it stops when it needs to stop, and when I turn the wheel, it goes the direction I turn the wheel. The fact that it has a radio or onboard Wi-Fi or Bluetooth or anything else, those are all dandy features, but fundamentally it still has to be drivable. Let's see, there are a couple other things I wanted to show you here. We talked about things out of scope. Let me bring up the threat model information dialog. I know when I review threat models, I like having this all filled out, especially this high-level description, because in theory, if you've written a really complete threat model, and you have the one paragraph elevator pitch for what it is it's actually representing, somebody who's never seen your product or service before and has never read your design spec should be able to understand what it is you've modeled. Assumptions, yeah, you can't threat model humans. Again, I mentioned about authenticated and authorized to drive the vehicle. External dependencies, the cellular carrier, the smartphone hardware and OS, the car application on the smartphone, your iPad, the app on the iPad, etc., etc., etc. I didn't articulate all the dependencies there for a vehicle. You could actually, if you're threat modeling a car from top to bottom, you need to include the oil, the brake fluid, the transmission fluid, the gasoline, etc., or diesel if it's a diesel vehicle. The other thing that I will show you, I haven't actually fleshed these out, but this particular tool, you change from, I just went to the view menu and changed from design view to an analysis view. It actually automatically generates your threats. Really cool. So let's see, spoofing the human user. We'll take the first one. Human user may be spoofed by an attacker. Now this is a threat against where the data flow between the human user and the manual controls and displays. You can see that highlighted in the diagram above. You'd either say it was mitigated. In this case, you might say it was mitigated because the user has possession of the fob, or it's not. But in this case, we'll say, okay, possession of the fob mitigates it, and then the tool very nicely says, gee, if you're going to say something's mitigated, you need to say why. So the beauty of this tool for me is that because it generates the threats automatically, the process of completing the threat model, the first step is to go through all the threats that are there and either say, okay, I've mitigated them or I haven't, they're not applicable, I need to investigate further or what have you. And the end goal, of course, is to have everything either mitigated or not applicable. Now, if you have something that needs investigation or not started, that may be a risk. It may be a vulnerability you're not choosing to mitigate, and that's fine. This is a way of assessing where you are with your design. Before I leave this, are there any questions on this particular part of my talk? Okay, I'll go back to slideware. And it would help if I'd remove the threat modeling tool from the screen. So we'll close that, go back to slideware. Success. So in summary, what makes an effective threat model? Accurate, unambiguous diagrams. Done to sufficient depth to thoroughly document what it is you're building. You've stated your assumptions. You know what your dependencies are. I picked on OpenSSL because it's an easy target, but it's a very appropriate, a very pertinent target because it is something that so many things use. And when it goes sideways, the internet tends to go sideways too. Your threats are well thought out. Your mitigations are chosen and implemented appropriately to actually address those threats. It's nothing worse than doing a great threat model and then choosing a mitigation that doesn't work. It gives you a false sense of security. Some resources. This is the latest Bible on threat modeling written by a good friend of mine named Adam Shostak, who spoke at this conference 2 years ago. At the time he was at Microsoft, my comment when he first talked to me about this project and then eventually got the book finished and published was that there were any number of us at Microsoft who could have written this book. The right one of us did. Adam has forgotten more about threat modeling than many of us know. Other resources, I mentioned the tool. There's the URL for it. In my bio, I talked about the security development lifecycle. There's the link to it. It's not any better or worse than others. It's a tool, a resource for your use. OWASP.org talks about threat risk modeling. Again, kind of the same idea. Let's go assess things and assess risk. Last year at DEF CON, which unfortunately I did not have the privilege of going to for a variety of reasons, but there were a couple presentations that are really pertinent to the example threat model I showed. One was playing with car firmware or how to brick your car. And this Italian guy went out and he found the physical connector behind the glove box for updating the car's firmware. Long story short, he managed to brick the car for 3 months. It was his girlfriend. My sources tell me it was his girlfriend's car. Not sure if she's still dating him or not. Apparently, he ended up taking the car to the dealer and saying, "What's wrong with it? It broke. It won't work." And it took him 3 months to figure out that they needed to replace all the electronics in it. I wish I had sat through that talk. It sounded like a scream. The slides, which are the link there, were an interesting read. Very much a sense of humor, tongue-in-cheek, and all that. But the bottom line is he bricked the car. The second one was a paper written by one of the directors of penetration testing at IOActive, and Charlie Miller, who is well known in fuzzing circles. I believe he's at Twitter these days. They basically wrote a paper that looked at automotive attack surfaces for about 15 different types of cars, and I mentioned tire pressure meters. They actually addressed that in that document. They found a vulnerability or a potential vulnerability where you could go in through some other system and get to the tire pressure gauge or the tire pressure meter. It was an interesting read. All right, any questions? Thank you. I did address your question, didn't I? Okay. All right. Well, if there are no further questions, I thank you for your attention. I also wanted to thank Alex and the rest of the BSides crew. This is year 3. I've been here all 3 years. We started out in a room about the size of had about enough chairs for these padded chairs up front. And now we're in a theater. Well done. Thank you.